Hi, I'm Dion Fafrut from Rohde Schwarz. I'm pleased to present to you a short video that we have prepared together with one of our customers on a test solution for digital verification and debugging of SpaceWire links. SpaceWire is a standard for high-speed links and networks used on board spacecraft. It is based on the IEEE 1355 standard and coordinated by the European Space Agency in collaboration with international space agencies such as NASA, JAXA, and Roscosmos, for example. And with that, I'd like to hand you over to my colleague.
Hi, I'm Matthias. I'm Matthias Beer, Product Manager for Oscilloscopes at Rohde Schwarz, and today we would like to show you briefly our instrument, the RTO, with a test setup we have prepared. We have here a demo board which is providing us data and a strobe signal, and we simply, for decoding the SpaceWire bus, we open our application cockpit and we select the corresponding protocol, in our case SpaceWire, and we see immediately that the bus is decoded. We can also make a single shot here. We can zoom into the decoding table so we get all the information from the measurement. We also have, in addition, the possibility to show the decode table of the bus to get additional information out of the measurement. This was the very brief demo, and I would like to continue with some results we have measured together with one of our customers, namely CTI in Brazil. They have been using the RTO digital oscilloscope for SpaceWire testing and verifying their ASICs for quite some time. And I would like to take this opportunity to welcome Daniel De La Sari from CTI in Brazil, who can present the use of the Rohde Schwarz RTO SpaceWire solution and the paper that he has presented at the 8th International SpaceWire Conference, which was held in 2018 in Los Angeles.
Hello, my name is Daniel De La Sari. I'm from CTI Brazil, and today we are here to talk about the debug of SpW links using a scope such as this one, RTO2000 series. Alright, so in order to debug the SpW link, it's good to understand that you have these many levels on the protocol layer. So when you have a problem, where are the problems? How to find them? Which tool do you use? So it's usually easier when the problem is only one layer, and it's a little more difficult when the problem is in multiple layers. On this presentation, we're going to talk about SpW DECODE, SpW character trigger, SpW EYE diagrams, SpW Data-Strobe SKEW, SpW activity correlated with power. And the message is it's good to have a tool which covers more than one layer. SpW DECODE. This scope, instead of just looking the signals high and low, you are able to select a protocol such as SpaceWire and use its decode capability. The way the scope works, it decodes what's in the acquisition window. SpaceWire, the way the protocol is built, has a challenge to determine the alignment, where each package or each message begins, since there is no regular space or a protocol violation that indicates the beginning of a packet. The parity bits are used in this case to align the packet. For this to work properly, it requires over 110 bits of error-free data. Then you can select if you want to see the results in graphic or table display, and you can also search on the waveform. Here's an example of the SpaceWire decode. The first two channels are the traffic going one direction. The other two channels are the traffic going other direction. So you can observe things like glitches or any problem because you have the analog wave. But here, down here, you also have the decoded waveform. So you can see a data 1A, EOP, that's end of packet, and then a new character. So you can see decoded message as well the raw signal where you can see if there is any problem. Besides decoding, the scope can also trigger on specific character. The way it works, it's a software trigger, so it works with a basic edge trigger. Then you have a SpaceWire decode phase, and then you search for that character. Combining all these steps, you have the SpaceWire trigger. The possible triggers we can select in this case are control character. You can select FCT, EEP, EOP, or any control character. Another option is to use a data character, and you can configure any value you want, and then you select to be equal, you select to be different, or it can be a range. You can also trigger on null characters. That's usually useful on the SpaceWire initialization, for example, not that much useful after that. You can also trigger on time codes. It's similar with data, where you can configure any value to be equal, to be different, or a range. And in terms of the SpaceWire errors, you can trigger on parity error or on escape error. EYE diagrams are very much used on high-speed communication because it's an indication, combined indication of skew and jitter. This scope has a hardware clock data recovery. It estimates the clock continuously in hardware, trigger on the recovered clock, and display the signal in persistent mode. It's much better than a software CDR because it's faster and because it delivers reliable statistics in a very short time, and also it reduces blind time. Many tests were done, performed over 100 measurements, where I used 10 different devices with different combinations between them, 200 megabits per second when possible, and we use different cable lengths, 1 meter, 3 meter, or no cable at all, and we use the scope auto set eye measurement. In this set of measurements, we are measuring the eye height, the eye width, and the Q factor. And here you can see an example with a 3 meter cable, where we have 2 transceivers and between them a 3 meter cable, and we got these results. This other screen shows the same case with a 1 meter cable, and even though the eye is open, it shows a possible impedance discontinuity, what may become a problem. And in this case, we have an example with no cable. It's a setup similar what's on the SpaceWire standard, and you can compare the values obtained in each one. It's also possible to set up a mask, and you can select which shape is the mask. In this case, we have a hexagon, and then you can put, according to the protocol, the heights and the deviations that you allow. And this one will clearly show any violators, and you can have statistics to quantify that. It means 1 error in 100 or 1 error in 1 million. And the statistics shows here how many you complete and how many you have on violation on the mask that you set up. And you can set up the mask according to the standard, as it was said before. SpaceWire protocol, it's critical for its Data-Strobe SKEW because it requires a minimum of separation between the data and the strobe edge. When it leaves the transmitter, usually you have a good separation, but as you go from the transmitter through transceivers, connectors, cables, boards on the other side, transceivers on the other side, you may have a skew. For 200 megabits per second, that may become a problem. So if you have a SpaceWire link, and it's very useful that you can measure and know on this particular link how much is my skew. Even though you may have data sheets from the transmitter, maybe on the receiver, but you don't have usually on all the parts, like including connectors and cables and everything. So this measurement will give an idea of all these parts combined. And again, we did many measurements on the receiver side using different devices, different cable lengths, and so on. On this work, two methods were used in order to do that. One that we call setup and hold, and the other one we call Mac XOR. Setup and hold uses scope between measurements. So you have something that you define as a clock, and the scope will measure the setup for another signal and the hold for the same other signal. For the SpaceWire, we select one to be the data, the other one to be the strobe, doesn't matter which one. And we set the clock slope to either because we want to measure skew of any edge to any edge. So in this case, as we are able to set up on the scope clock slope to either, you're going to be able to measure, this could be a rising edge like you see on the picture, or could be a falling edge. And here you also are measuring any transition on these other signals, so could be rising edge or could be falling edge. So in summary, you're measuring any transition on clock to any transition data. This is method 1. Method 2, we take the data signal, the strobe signal, and we do a mathematical function like a logic XOR between them. And then we measure the XOR high or low duration, because as you have a skew on this edge, for example, if the strobe edge occurs earlier, it means that this pulse, this transition will be earlier, and it means that this pulse will be wider. So as you are measuring the width of this pulse, if it goes much beyond the 5 nanosecond standard for 200 megabits per second, you are seeing that this edge is having a deviation, and you can know how much is the skew. In order to know the skew, is a very simple math. In the first method, we take the maximum measurement of setup and hold and subtract the bit period for that particular link. And in the case of the mathematical XOR, we take the maximum of the high pulse and we subtract the bit period. And all these measurements we perform with the statistics enabled on the scope, and usually we accumulate over 10,000 events in order to have some good statistics. Here's an example how the screen looks like. We cannot see the signals behind, but we can see the measurements here. You have the setup and the hold that was mentioned before for channels 1 and 2, and you have here the positive pulse. So it measures the maximum value, the minimum value, average RMS, and so on. And below here you have the same measurement but for channels 3 and 4. So by doing this you can collect and know your link, how much skew you have. That's the graphical view of the setup, where you have different transceivers. In this case we call it T6 and T1, and the measurements were here. And if you want to collect the receiver side, that would be channel 3 and 4 in this case. And by doing all this measurement, we conclude the difference that we had between method 1 and 2, it's smaller than the probe bandwidth. So we conclude that the two methods are useful. There's no need to measure them in both ways, but you can select one of these two and measure on that way. This other screen shows another capability of the scope when you use a different probe that's a multi-channel power probe. In this case, you can correlate different signals on the spacecraft, for example, SpaceWire signals with power signals or current signals and so on. And here in this example, when you have activity, you see that the power is higher. As soon as we force an error in this case, and then you can see the power decreasing. One side is trying to connect, the other one is not answering for this time. And doing so, you can correlate digital signals, SpaceWire signals with power signals such as voltage, current, or power. This other screen shows an example for a link initialization. So you have here that where you need over 110 bits of error-free data, and then you select a place where you want to zoom, and we select exactly the initialization. So both links, both sides were communicating at 10 megabits per second, and you can see the exchange of nulls and FCTs until it reached the run state, so you can switch to 200 megabits per second, and you can zoom at any place you want, and you can select exactly what calls the state machine to get in the run state, for example. So our conclusion is that the scope is very useful to debug space-wide protocol lower layer issues. So in this presentation we saw the space-wide decoded capabilities, where you can see on the same screen the decoded characters together with signal integrity signals, looking for signal integrity issues such as glitch, transition time, and so on. We also saw that you can trigger on space-wide character, what's very useful to find a particular event that's occurring rarely in your communication. We also shown the same scope, the same one that you can see decoded signals. We also show the capability to see eye diagrams, where usually you do that to monitor the link qualities and the margins that you have in your communication. Very critical to space-wide, we show Data-Strobe SKEWs, and you can also, you can also do LVDS measurements and save your work, because that's a very easy measurement for a scope to do. Okay, so that's our presentation, and where we show all these examples why this scope is very useful to debug space-wide links. Hi, now we are here with a hardware setup in order to see some examples that we saw in the presentation. We have the same scope. We have differential probes from Rohde Schwarz. One probe can directly monitor like a data signal because it takes the plus and the minus. And also we have an ASIC that was developed at CTI by members of CTAR team. And we have a space-wide cable between them. So using this setup, we're going to be able to see many characters on this space-wide link. So now we have the scope screen with two space-wide signals, the yellow and green. Here you can see the overall, and we are zooming on this small region. And here is the decoded data that this scope can decode space-wide characters like we saw in the presentation. Now we're going to talk about the triggers. In this case, we're triggering on the FCT character. And we can go here and change, that's a type of a control frame, and change, for example, to EOP, which is end of packet. So now we have a end of a data packet here, 35, 34, 33, and then the end of packet marker here. For this demo, we on purpose put some errors built in, so we can also trigger on EEP, which is the end marker with an error. So now you can see here the EEP. The first one we saw, the FCT, is a token for flow control. The scope also had the option of any, but we saw 3. Now we can trigger on a specific data, for example, 26 hex. So we have a 28, 27, and then we're triggering here on 26. And we could select other values as we want. But let's go to a different type, which could be useful for initialization. You were triggering on null character. Another example, we can trigger on time codes. For example, we're triggering on time code 46, what can be seen here, and that's the trigger, and that's the value, and so on. So you can see you can change and debug your link, changing the triggers to whatever you need. Now let's change the setup to see something else. I have some built-in setups here, so I select one for EYE diagram, and you have to come here and do a scope auto set, and then I can put them with the same vertical value. So I have an EYE diagram here with some like height, width, Q factor, rise time, fall time, whatever I want to measure. There's many options. If I want to see the yellow or the green, and then you can, for example, debug what's this transition here, because that's not expected. We also during the presentation talk about SKEW and LVDS. So here we have a lot of measurements like that setup and hold that was used for calculation of SKEW. Also for calculation of SKEW we have the math, so we measure here positive pulse, negative pulse. I'm going to stop so we can see a little better. And LVDS signals, we have high value, low value, amplitude, rise time, fall time, and whatever channel. And because it's statistics enabled, you can see the RMS, you can see the maximum value, minimum value, and so on. So this is an example of some things we saw in the presentation.
Thank you, Daniel, for a very informative and interesting presentation. If you should have any further interest or questions on the Rohde Schwarz SpaceWire test solutions, please do not hesitate to contact our local representative or Rohde Schwarz directly.